Welcome to Chapter 4, Section 3, Derivative Testing for Max and Min. In this section, we're going to continue to look at relative extrema, or in other words, local extrema. Those names are synonymous. And we're going to look at a new way to test to find if a point is a local max or min. And so let's go back to our current definition of local extrema. And remember, this is the same thing as relative extrema. We use both interchangeably. And a local min or a local max, or relative min or a relative max, is just basically where at that point it's bigger than anything else around it or smaller than anything else around it. So a local max, we go from increasing function to decreasing function, and a local min, we go from a decreasing function to an increasing function. And that's one of the ways that we've found our local extrema up into this point. Or another way we can say is our derivative, our f prime, goes from positive to negative to find a max, or our f prime goes from a negative to positive to find a max. And those points happen when f prime of x is equal to 0. And that's what we found up into this point, when f prime of x is equal to 0. Well, they also happen when f prime of x does not exist or is undefined. So either of these two cases is where we're going to find our local or our relative extrema. Now, those points are called critical points. The critical points are where f prime is either not defined or equal to 0. And so we're going to be asked to find critical points and talk about, are those actual points on the graph or are they undefined points on the graph. So let's take a look at this first function, f of x equals x cubed minus 9x squared plus 24x minus 10. And we want to find the critical points, so let's see, where is f prime of x equal to 0? Well, we need f prime of x first. So that's going to be 3x squared minus 18x plus 24. Okay, so this is a quadratic that we're going to set equal to 0. We're going to try to solve. And first, let's simplify the quadratic by dividing everything by 3. And when we do that, we end up getting x squared minus 6x plus 8 is equal to 0. And so in solving this quadratic, we get x equal to 2 and x equal to 4. Okay? And so these are our two critical points. But before we move on, we have to ask ourselves, is f prime of x ever undefined? So is there a point where x squared minus 6x plus 8 is undefined? And it's a quadratic, and so we know, no, it's defined for all real numbers of x. So therefore, these are the only two critical points. And if we look at the graph, we see that they are the two critical points at 2 and 4, and 2 happens to be a max, 4 happens to be a min. Now, we could have found that by looking at a valuable chart and looking at where is f prime. It goes from positive to negative before 2, and it goes from negative to positive over 4. But we're going to look at another technique on how we can determine that those are max and mins without graphing or without looking at the sign change of f prime. So that's going to use the second derivative test. Now, we know the second derivative tells us a little bit about concavity. It tells us if f double prime is positive at a given point, then we're concave up. If f double prime is negative, then we're concave down. Well, we can do this for our local extrema. We can just plug those points in, and we can find, are we concave up or concave down at that point? Well, if we're concave down at an extrema point, then that means it's a max. And if we're concave up at an extrema point, that means it's a min. All right, so essentially all we're doing is we're taking our critical points and we're evaluating f double prime at that point and seeing what happens. Now, this is not a totally conclusive test. If by chance you evaluate f double prime at a given point and you get it equal to 0, then it's inconclusive. That point may be a local min, could be a local max, could be neither. So what does that tell us? We've got to go to other tests. So looking at the change in sign of either the f prime or looking at the graph. So this is a quick and easy test to check, and it'll work most of the time, but doesn't work all the time. So if you get f double prime of a value equal to 0, then you got to use another method. Okay, so let's give this a shot. Let's try some of these out. Let's go back to our other function that we had earlier where we know the critical points are 2 and 4. All right, well, we can test this using f double prime. So we've got to find f double prime first. And let's rewrite up f prime was 3x squared minus 18x plus 24. And so f double prime of x is simply going to be 6x minus 18. And so if we want to evaluate at f double prime of 2, when we put that in, we get 12 minus 18 is a negative 6. And so that tells us that since this is concave down, that this has to be a max. And evaluate f double prime of 4, that gives us 24 minus 18. That gives us a positive 6. And so this has to be a min. All right, so it's a quick and easy test to see, is my critical point a maximum or a minimum? So let's try another one here. And we're going to take a problem out of our book, looking on page 255, and we're going to look at number 19. Now, number 19, we're actually given f prime of x is equal to x cubed times the quantity x squared minus 5. And so we're asked to find all the critical points and determine whether they're maximums or minimums. Okay, well, critical points are going to happen when f prime is either equal to 0 or undefined. Since it's a polynomial, there are no points of discontinuity, no points of non-differentiability. So therefore, we're only going to happen when x, or f of x prime, excuse me, is equal to 0. So we set this equal to 0, and so that means x equals 0 for this piece, and that means that x equals plus or minus radical 5. And so these are our 3 critical points. Now, in order to find whether they're maximums or minimums, we need to find f double prime. So I'm actually going to rewrite this function to say that it's x to the 5th minus 5x cubed. Now, why am I doing that? That way I can avoid doing the product rule, and when I take the derivative, I just get 5x to the 4th minus 15x squared. And so we simply have to evaluate at each of these points. Well, f double prime of 0 gives us 0. So therefore, that tells us that we don't know what that is, and we're going to have to look at that in another fashion. All right, we're going to come back to that. Let's look at f double prime of radical 5. Well, when we put that in, radical 5 raised to the 4th power is just 25. 25 times 5 is 125. And then we want to subtract, and 15 times x squared here, when radical 5 is squared, that gives us a 5. And so that's minus 75. So what this tells us is that we have a positive number. So that means that radical 5 is concave up. So therefore, radical 5 is a min. Well, let's look at negative radical 5. Well, negative radical 5 actually isn't going to change anything, because when the negative is raised to an even power in both of these, the negative goes away. So that means negative radical 5 is a relative minimum. So let's go back to x equals 0, the critical point of x equals 0. And we have to determine, is that a max, a min, or it could be neither. Well, the second derivative test here was inconclusive because it gave us f double prime of 0 is 0. So let's look at f prime to the left and right of 0. So talking about f prime up here, this one up at the top, okay, if we put in a number, say like negative 1, negative 1 squared minus 5 is a negative 4, and negative 1 cubed is a negative 1, that gives us a positive number. And if you put in something like a positive 1, 1 squared minus 5 is a negative 4 times 1 is a negative. So if we're going from positive to negative, meaning we're increasing to decreasing, that tells us that 0 is a relative max. So in this problem, the second derivative test was able to get us 2 out of 3. So it got us 2 out of the 3 possible critical points but the third one we had to resort back to other methods to determine what type of extrema it is. Now let's take a look at number 28. Number 28, we're given the function f of x is equal to x to the fourth minus 2x squared plus 7. And we want to find all critical points, and we want to use any method that we choose to determine what type of critical points they are, whether they're max, min, or neither. So let's find f prime of x, and that's simply 4x cubed minus 4x. And we set that equal to 0. Factor this, we get 4x and x squared minus 1 is equal to 0, so that happens when x is 0, 1, and negative 1. Those are the three critical points. And once again, it's a polynomial. There are no points of discontinuity or non-differentiability, so we only have critical points at these 3 points where f prime is 0. So let's try the second derivative test, see if that works. So what is our second derivative of x? Then that's going to be 12x squared minus 4. So if we put in 0, we get a negative. So because 0 minus 4 is negative 4. So if that's negative, it's concave down, meaning 0 is a max. So f of 0 is a relative max. We put in a 1, we get a positive. So that means we're concave up. So at x equals 1, we are a relative min. Put in a negative 1, we still get a positive because negative 1 squared is 1 times 12 minus 4 is still a positive 8. So negative 1 is also a min. So in this case, the second derivative test was able to get all of our critical points, and so we can do it much more quickly than doing a variable chart for f prime. One last one, let's take a look at number 16. Okay, number 16 is a little more simple in that we're just finding the critical points and identifying whether they are stationary points, meaning is f defined, or simply stating that the function doesn't exist or the derivative of the function doesn't exist at that given x value. So let's take a look at number 16. Number 16 has a function f of x equals x to the 4/3 minus 6x to the 1/3. Okay, so when we take the derivative of this, we just use our power rules here, and we get f prime is equal to 4/3 x to the 1/3 and minus 2x to the negative 2/3. Alright, so we're going to have to use a little algebra here, and I'm going to let you do the algebra on your own. And when you simplify this, you should get f prime equal to 2 times the quantity 2x minus 3 all over 3x to the 2/3. Now, why do I want to use the algebra to simplify this? Well, it's because this can help me determine when is f prime equal to 0 and when is f prime undefined, because those are where my critical points are. Well, when is f prime equal to 0? That's when the numerator is going to equal 0, and that's when x is equal to 3/2, because 2 times 3/2 is 3, 3 minus 3 is 0. That gives us a 0 in the numerator or a 0 for the entire function. So this is a critical point, and it's stationary. Why is it stationary? Because our function is defined here. That's just when f prime is equal to 0. However, the other critical point is x equals 0, because putting a 0 in for x, we get a 0 in the denominator, and that can't happen. So f prime is undefined at x equals 0. So therefore, it is a critical point. Now, if we wanted to determine what are those critical points, are they relative maxes or mins, we could use either the second derivative test or previous methods. But in this case, all we had to do is identify the 2 points, state that 3/2 is stationary, and 0 is where the derivative of the function does not exist. Alright, so what I want you to do is try 4 problems here, and actually you're not going to do 16, you're going to do 15, 23, 25, and 27. And come into class with those done and any questions. Thank you.